So in this lecture we'll understand the hydrostatic law. So this is the x-axis, this is the positive x-axis, this is the negative x-axis, and this is the y-axis, positive y, negative y, this is positive z, this is negative z. And there is a fluid, it is a static condition, so this is the static symbol, shear stress that is equal to 0 and acceleration that is equal to 0. In vector form, that is ax I cap plus ay j cap plus az k cap. And we know that summation of F net that is equal to m into a. So F net means this is due to pressure force, gravity force, viscous force. That is the Navier-Stokes equation. So F net, so Fp pressure force, Fg gravity force, Fv viscous force, that is equal to m into a. So Fp is the pressure force, Fg is the gravity force, and Fv is the viscous force. Okay, so the gravity force that is equal to m into g, we know that m equal to rho into dv, this is a small element, so that's why this is a small change in volume, and that is into g. Okay, so this is Fg. Okay, now so here this is x axis, this is y axis, and this is z axis, and this is the small element, fluid element. So mg is downward direction, mg, and this is dx, this is dy, and this is dz. Okay, so in positive x direction, so the pressure will be P minus del P by del x into dx by 2, and what is the area? Area will be dy into dz. So dy into dz. So this will be in this direction, positive x direction. So in negative x direction, that is a P plus del P by del x into dx by 2 into dy dz. Okay, so similarly for y direction and for z direction. Now for g we know that gx I cap plus gy j cap plus gz k cap, but here the g is acting downward direction, so that's why g is minus g k cap in z direction. So that's why the another x and y are 0. Okay, so gravitational force acting on the z direction, that's why these two are 0. So from Taylor series expansion, we know that f of x plus dx that is equal to f of x plus 1 by 1 factorial del fx del x into dx plus 1 by 2 factorial del square fx by del x square dx plus dot dot dot. So we neglect the higher order term. So for x direction, if we want to calculate the pressure force in x direction, so in positive x direction, so this is the positive x direction, what is the pressure force? P minus del P by del x into dx by 2 dy dz. So this is the P minus del P by del x into dx by 2 dy dz. And for negative x direction, this is negative, so P plus del P by del x into dx by 2 dy dz. So minus of P plus del P by del x into dx dy dz. So from here we can get Fpx that is equal to minus of del P by del x into dx dy dz. Okay, so from here Fpx that is equal to minus of del P by del x into dv. So here Fpx that is the pressure force at x direction, Fpy that is the pressure force at y direction, Fpz that is the pressure force at z direction. Okay, so similarly Fpy that is equal to minus of del P by del y into dv, and similarly Fpz that is equal to minus of del P by del z into dv. Okay, so pressure force, total pressure force, that is Fpx plus Fpy plus Fpz. So Fpx, we see that Fpx that is to minus of del P by del x into dv. So minus of del P by del x into dv, minus Fpy that is minus of del P by del y into dv. So minus of del P by del y into dv, and Fpz minus of del P by del z into dv. Okay, so in vector notation, so minus of del P by del x So the pressure force that is equal to minus of del p by del x into dv I cap minus of del p by del y into dv j cap minus of del p by del z into dv k cap. So that is equal to you can say that del x I cap plus del y j cap plus del z k cap into p dot v dv. Grad that is equal to del x I cap plus del y j cap plus del z k cap. So pressure force that is equal to minus of divergence of p into dv. Okay, so pressure force plus gravity force, there is no viscous force, that is equal to m into a. So pressure force that is equal to minus of grad dot p dv plus rho dv into g. So mg fg gravity force that is equal to rho dv into g. So that is equal to rho dv into area, sorry, acceleration. So for a static fluid, the acceleration that is equal to 0. So from here that is minus of gradient of p plus rho g that is equal to 0. So this is the vector equation. So from here minus of del p by del x I cap plus del p by del y j cap plus del p by del z k cap plus rho into gx I cap plus gy j cap plus gz k cap that is equal to 0. So minus of del p by del x, so same here, plus rho into, there is no gravitational acceleration in x and y direction, only z direction, and due to this downward direction the sign is negative. So minus g k cap that is equal to 0. So for x direction, from this equation you say that minus of del p by del x plus rho of 0 that is equal to 0. So from here del p by del x that is equal to 0. Okay, and for y direction in that equation, so del p by del y that is equal to 0, and for z direction from this equation minus of del p by del z k cap minus rho into g that is equal to 0. So from here del p by del z that is equal to minus of rho g. Okay. So now, so as per Cartesian system, so this is the this is z equal to 0, this is a z equal to 0 pressure line at atmospheric pressure that is equal to 0, and this is a positive, here this is one point, you have to calculate the pressure at that point, and here there is another point. So this is the positive z direction, and this is the negative z direction. So here p proportional to minus z, okay, and dp that is proportional to minus dz. So for that case dp by dz that is equal to minus rho into g. Okay, so dp that is proportional to minus dz, so that's why dp by dz that is equal to minus of rho into g. So this is applicable for compressible or incompressible both. Okay, so for incompressible fluid, if there is incompressible fluid, okay, so rho not equal to function of pressure, so for that case dp by dz that is equal to minus of rho into g. So from here dp by rho that is equal to minus of g into dz. So from here minus 1 by rho 0 to p, okay, dp. So p is changing here 0 to p, that is equal to minus g, z equal to 0 to minus z. So here z equal to 0 to minus z, so 0 to minus z dz. So from here you can get p equal to rho into g into z. So this is very, very important. So pressure is increases as depth is increases. For pressure system, so h equal to 0, p atmosphere that is equal to 0, you have to calculate the pressure at that point, at this point. So this is the negative h and this is the positive h. So here pressure is proportional to h. So in that case, so pressure that is proportional to h, so dp that is proportional to dh. So dp by dh that is equal to rho into g. So this is applicable for compressible or incompressible both fluid. For incompressible fluid, rho not equal to function of pressure. So from here integration 0 to p dp that is equal to rho g integration 0 to h dh. So from here you can get that is p equal to rho g h. Okay. So now For absolute pressure, suppose there is a wall, this is wall, and here there is a fluid in left hand side. So this is the left hand side, and there is a fluid is there, and the fluid is in rest. So there is a fluid, and this fluid is in rest. So this is the wall. The height of the wall, that is h, and this is the positive h direction, lower direction, that is positive h. Okay, so the atmospheric pressure, that is almost constant in that depth, because this depth is very very less. Okay, so atmospheric pressure almost constant, but due to that fluid the pressure is increases as depth is increases. So here this pressure equal to rho g h into p atmosphere plus p atmospheric pressure. So we know that dp by dz, that is equal to rho into g. So from here, that is integration p atmosphere to p. So here there is a p atmosphere, and you have to calculate here in that location, so p p dp, that is equal to rho g 0 to h. So in h location, so 0 here to h, so rho g 0 integration 0 to h dh. So from here you can get p, that is equal to p atmosphere plus rho g h. So this is very very important. So here p proportional to h. Now let's try to understand one question. Assuming constant temperature condition and air to be an ideal gas, the variation in atmospheric pressure with height calculated from the fluid static is. So it is what? So assuming constant temperature condition and air to be an ideal gas. So we know that dp by dz, that is equal to minus rho g. So dp by dz, that is equal to, from ideal gas equation, pv equal to mRT, we know that. So p equal to rho RT, rho equal to p by RT. So p by rho equal to p by RT into g. So here integration p atmosphere to p dp by p, that is equal to minus of g by RT. So g by RT into integration 0 to z dz. Okay, so dz is coming in this portion. So ln p by p atmosphere, that is equal to minus gz by RT. So p equal to p atmosphere into e to the power minus gz by RT. So here there is exponential is there. So the variation in atmospheric pressure with height calculated from the fluid static is, the answer will be exponential. So the answer will be exponential. So okay, thank you.